All right, so is everybody working on their second go on the exam? All right, remember you have until 11:59 tonight to submit that if you decide you want to. All right. Next week we'll start in with the normal schedule. We'll have new assignments, homework assignments, and SI and TF office hours, and all that stuff will be starting again next week. Okay, let's quiet down, please. We started yesterday in chapter 16, talking about resonance, conjugation. Okay, let's quiet down, please. And today what we're going to do is we're going to look just a little bit more of some specific resonance situation, and then we're going to look at some reactions that involve resonance and involve Dienes. Okay? Next week we'll probably finish 16 today, and next week we'll start into chapter 17, which is on benzene and aromatic compounds. Okay? All right, so let's start out with the clicker. Record. We're going to pick up by looking at some allyl cations and try to predict their relative stability. Yeah. I can move that. Let me just look this. All right, so let's look at the structures across the top.
Question, are you recording today?
I am recording today. Thank you. Yep. It's your second reminder. You guys keep on me and I'll make sure they're all recorded. I apologize for yesterday. So let's look at the ones across the top. All right, so which of those structures in the top three, let's quiet down, would be the most stable? The first one on the left? No. The middle one? No. The one on the right? Yes, right? So this one over here is going to be the most stable, okay, because it has the carbocation on an atom adjacent to the pi bond, right? That allows those electrons to be delocalized, and so that plus charge is spread over two different carbons, okay? What about the other two? Do you think we can say anything about the relative stabilities of those carbocations? Well, the carbocations are both essentially just secondary carbocations, right? And because this carbocation is isolated from the alkene by an sp3 hybridized center, it doesn't gain anything from resonance. If we look at absolute energies, then I think the one in the middle would be more stable than the one on the left, just because sigma bonds are usually stronger and more stable than pi bonds. Okay? But we'll just say that these are probably about the same stability as far as reactivity goes. All right? So let's look at the three in the middle, and let's determine which of those would be most stable. Okay, this gets a little bit trickier, right? So whenever we see allyl cations, we need to make sure to take into account both of their possible resonance contributors. Okay, so let's draw out the resonance contributors for these allyl cations, right? So the pi bond always moves towards the plus, and so this would give us a contributor, a resonance contributor like this. In the middle one, again, the pi bond moves toward the plus. And so we get plus like this. All right, so what about on the left? Does that make a difference in your impression of the stability when we draw that second resonance contributor? Yeah, clearly, because at first, the first thing you think is you go, oh, it looks primary, right? Oh, that must be super unstable, right? But when we draw the resonance contributor, all of a sudden you see that that plus is spread not only on that primary position, but also a tertiary position. And so by adding, so essentially we have a tertiary cation that's also allylic. And so that makes it even more stable than a normal tertiary carbocation. Yeah, question?
In the past we've seen hydrogen shifts to promote the stability of a carbocation.
Mm-hmm.
Is it possible to have a hydrogen shift to ensure that a carbocation is in an allylic position, or no?
Okay, so the question is if we form, so like the upper left, right? Question is, because this is an isolated carbocation over here, right? This one's isolated from the pi bond because it has this sp2 hybridized center. So the question is, could we get a 1,2 hydride shift to move the carbocation to the adjacent position so it could become allylic? I think that is possible. Yep. All right, so we want to judge these stabilities. So let's look at the bottom first. And this kind of gives us a position of where an allyl cation fits into what we already know about relative stabilities of carbocations. Okay? As we know, for normal carbocations, as it becomes more substituted with alkyl groups, it becomes more stable. Right? So we go from methyl on the left to tertiary on the right. Okay, that's what we learned last semester. So the allyl stability here, notice that this allyl cation here is essentially would be delocalized between a primary position on one side, and if we drew its resonance contributor, what would be the substitution on the other end? Primary as well, right? So this is kind of between two primary positions. And what they say is that that is about the same stability as a secondary carbocation. Okay, so by adding this double bond, we've essentially jumped one position in stability. Okay? So if we think about the structures that we have across here, here we have a allyl that is spread between a primary and tertiary, right? So that's clearly going to be more stable than the tertiary. So this, if we're ranking these in stability, then this one would be the most stable. Okay? Now, these other two are a little tricky because we essentially have between a secondary and a primary, and we just have a normal tertiary over here. Okay? Our old text used to, in fact, have this equal to tertiary. Okay? So it had it even more stable. So I think it's going to be a little hard for us to tell if we have primary to secondary versus tertiary, but in my impression and understanding over a few years, usually if we have an allylic system like this, especially one that has a secondary or tertiary on it, that's going to be more stable than just a normal isolated tertiary carbocation. Okay, so we can say that these are going to be maybe close, but we're going to give the nod to the allylic one. Okay, so this might be a little more stable. So this is going to be number 2, and this is going to be number 3 over here. This is number 1 over here. Okay, and if we're doing reactions and stuff, I'll try not to push you to make this kind of decision. I'll try to make it more clear than that. All right, does this make sense? Saw already that they don't actually have in this chapter, but I'm going to include it in here because it's very much the same is this one that we call the benzylic cation. Okay, and we drew some resonance structures yesterday showing how this plus on the position next to the benzene ring could be delocalized around the ring. Okay, and so this benzylic one is definitely going to be more stable than this secondary over here. Though I think this is a system that was asked about on the other one, whereas if we have a system like this, you know, we could also get a 1,2 hydride shift if this was a real reaction, which would then lead us to this benzylic carbocation. Okay? So allylic and benzylic, the benzylic is roughly the same stability as the allylic as well. Okay? So let's to some reactions. Okay? So we're going to predict products for the reactions of conjugated olefins, conjugated alkenes. Presents kind of an interesting situation. All right, so let's just look at a series of reactions here. On the top one, we have HBr. So when we have benzene rings at this point, until we start into the next couple of chapters, if we have a benzene ring, the reaction is not going to take place within the benzene ring. Okay, the benzene ring would be there as a way to add resonance. Okay? So if we add HBr, right, the first step would be protonating the double bond, just an electrophilic addition reaction you guys learned before. Where would the carbocation want to form? As far as the two choices between those, the one next to the benzene ring, right? So we'd get the carbocation there. I'm just going to kind of shortcut this. We'd want the carbocation here, so that's where the bromine would come in. And so this would be a regioselective reaction with the bromine at the benzylic position. Okay, because that's the more stable carbocation. It would be at that benzylic position. Okay? All right. The next one down is an isolated diene. Right? So the two double bonds are separated by several sp3 hybridized centers. Okay? So there's no resonance between them. If we added HCl to this, and only one equivalent of it, where would the reaction take place? Right, on the alkene on the left. Right, so again, it's going to protonate the double bond that can lead to the most stable carbocation intermediate. All right, and that's going to be the tertiary one that forms on the left. So again, this would be regioselective, and we would only get the chlorine, or predominantly we would get the chlorine at that more highly substituted position. Okay, because that's where the more stable carbocation is. What if we had to add an excess? So we add at least 2 times of HCl, or even more. Then we'd get 2 reactions, essentially acting independently of one another. Okay, so then we could get a chlorine here and a chlorine here. Right? So we just have 2 separate reactions. Okay? Now let's look at the conjugated system. All right? So, like we would predict from up above, we could just add, okay, I'm going to simplify this. I can't really erase this, but let's just imagine these 2 methyl groups are not there for right now. Okay, so just X those out. We just have 1,3 or buta 1,3 diene. Okay, so we could add HBr onto one side, and we get this product. So we add the H on the end. Bromine goes to where the carbocation is. However, there's another product that can form in this reaction. Okay, and that is the double bond shifted here and the bromine on the end. Okay? So if we look at where the new H goes, so this H went here, okay, we call this product the 1,2 addition product. Okay, in this molecule, it does turn out to be that those, if we were counting this, well, 1,2 essentially means that the H and the Br are going on adjacent carbons. Okay, not necessarily a 1 and a 2 if we were naming it. All right, if we were naming that, we'd start with the alkene. Yeah, question?
Yeah, can you just show the mechanism for that PAR, the PAR right bromination?
Yeah, we will on the next slide. I know, sometimes it's hard to wait, isn't it? So exciting and suspenseful. All right, on the right structure, the H came in on the same position, and the bromine ended up on the other end. So this is 1, 2, 3, 4. So this is called a 1,4 addition. Okay? All right, so we get a mixture of these two products. All right, so let's look at how this takes place. All right, so let's just do the same thing again. Let me just show you something even more interesting about this first, though, and then we'll talk about how it takes place. Okay, so I'm just going to rewrite these two products. So there was our 1,2 addition. 1,2 plus 1,4. All right, now the ratio of these two products is not always constant. It depends upon the reaction conditions. All right, so if we do this reaction at a, what we're going to call a low temperature, so this is going to be cold. I'm going to put this, they put minus 80 in the book. I'm going to change it just a little. I'm going to say, just to make it interesting, minus 78 instead of minus 80. Minus 78 is a common temperature for cold reactions. Okay? Doing it in the organic lab, a lot of times, if you read about them, a lot of times you'd be at minus 78. Anybody have an idea why this presumably arbitrary temperature?
Isn't that the temperature of liquid nitrogen?
No, it's not the temperature of liquid nitrogen. That's down at minus 200 or something like that. Okay, so that's really cold, but it's good idea. Okay, minus 78 happens to be the temperature you get when you mix dry ice into acetone. Okay, so that is dry ice, so solid carbon dioxide and acetone. Okay, so you mix those up into kind of a slush, and it goes to minus 78. Right? In fact, you can do dry ice with different solvents too, chloroform or different solvents, and they all have different temperatures, and so that's one way you can create different types of temperatures, is just these different cold baths. Just a little side thing. All right, if we're at low temperature, then we get an 80% to 20% ratio of the 1,2 addition to the 1,4 addition. All right? However, if we go to a warm temperature, and they just kind of pick something like 40 degrees Celsius, then the ratio reverses itself. Then we get 20% of the 1,2, we get 80% of the 1,4 addition. Okay, so we can adjust the product that we get by varying the temperature of the reaction. Okay, so that's pretty cool, huh? All right, so let's try to figure out why. Okay, so let's look at a mechanism for the formation of both of these products, and that'll start to lead us in the right direction. Okay, so what we're going to do first, like any electrophilic addition of an alkene, the first step is to protonate the double bond. Okay, and just like with any other alkene you've ever worked on, we're going to protonate the diene to yield the most stable carbocation. Okay, and so for a simple structure like this, we're definitely going to protonate, and this is going to be true for all dienes. We're going to protonate on one end or the other. Okay, and why would that be? Because it would lead to an allylic carbocation. Okay, if we protonated on one of those two intermiddle carbons, then it would put the carbocation on the end and there would be no resonance. Okay, so we're always going to protonate on the end. Okay, so I'm going to draw it like this. We protonate like that. Leads us to a carbocation like this. Okay, so it's secondary and it's also allylic. Right, so let's draw out its resonance contributor as well. Okay, so resonance can be like this. Oops, we can bump that bond over like that. And so we have another resonance contributor like this. Right, so remember, this is essentially a single carbocation with that plus charge spread out over those two carbons. All right, so when the nucleophile comes in, the bromide comes in, it can be attracted to either of the positions that have the plus on them. Right, so we can easily get to, oops, come on, to this position, to this product, the 1,2 addition product. If we just have bromide here, and it comes in and attacks that kind of the first carbocation that we drew, right? That gives us the 1,2 addition. So how do we get to the 1,4 addition product? The bromide comes into the other end of the allylic carbocation, right? So we can get to the other one, let's draw it over like this, by having this bromide come into the other end of the carbocation. Okay, so that's how we get there. That doesn't yet tell us why we would get different ratios of those two products at different temperatures, right? And so in order to try to understand that, we have to consider the different energies and how the energies change during this reaction. Okay, so let's look at a reaction coordinate or reaction energy diagram. Okay, so there's two things going on. One, it has to do with the relative energies of the transition states. Okay, if the reaction is controlled, if the main product is the product that gets formed the fastest, then we need to look at the transition states. Okay, so these control the reaction rate. Okay. However, we have a different situation down here, right? If we're going to look at if the main product that forms is the one that's more stable. Okay, so this has to do with product stability. Okay, reaction rate has to do with kinetics, right? Product stability has to do with what? What would we call that? Starts with a T. Thermodynamics. All right. So it happens that if we run this reaction at a cold temperature, essentially the reaction can go to products, but it's irreversible. There's not enough energy in the system for these products to go backwards over that hump back to the intermediate. Okay? So that's the first thing. Cold temp, the reaction will be irreversible. Okay? That means if it's only going to go in the forward direction, then it has only to do with kinetics, and the main product is going to be the one that has the lower energy transition state, that's formed faster. Okay, so then we could say the main or the major product is the one that's formed faster. Is, oops, I'm going to run out of space here, is the one that's formed faster. Okay, this kind of manifold or something is what we call kinetic control. Okay, it's only the kinetics, the rate of the reaction, that's controlling the product ratio. Okay? If we do this at a warm temperature, now there's enough energy in these products to go backwards and go over that hump back to the intermediates. So at a warm temperature, this reaction becomes reversible. Okay, so this one is reversible. So that means it's under equilibrium. And when we're in equilibrium or under equilibrium conditions, we just get more of the product which is the most stable. Okay, so we just get the most stable product. So the major product is the most stable one. Okay, this is what we call, I'm just going to, thermodynamic control. All right, so the next part of this is, though, we have to figure out why it is that the pathway leading to the 1,2 addition product is the one that has the lower transition state. Okay, why is that formed faster, and why is it that the 1,4 addition product here is the more stable one? Okay? So, the kinetic control doesn't so much have to do with the structure, but it has to do with the fact that when the molecule becomes protonated, let me write this off to the side here. So let's draw what this would look like after the initial protonation. So we've added this H, say there, and we've broken the bond between the H and the bromine. So the bromide would be sitting here right next to where the H was, spatially. And we've generated a plus right here. Turns out that the fastest formed product is the one where the bromide reacts with the end of that allylic carbocation just that it's closest to. It's what they call the proximity effect. Protonates, it just bumps right into the cation on that end. It's just all about spatial orientation. Okay? So this goes to the closest end of the plus. Okay? This is the proximity effect. Oops, effect. And so that's why kinetic control at cold temperatures always gives the 1,2 addition. Okay? We'll see that there could be different cations. It's always going to protonate at the position to form the most stable carbocation, but then the bromide is always going to do a 1,2 addition if we're at cold temperatures. Okay? If we're at warm temperatures, so if we look at these two products, how would we judge which one of these is more stable? Yeah.
Substitution about the double bond.
Exactly. So what's going to control the stability here is the stability of the alkene, right? And you learned before that more highly substituted alkenes are more stable. Okay, so notice that this 1,4 product has 2 alkyl groups, and we call this a di-substituted alkene. Whereas the one up here has only 1 carbon attached to it, and 3 hydrogens. This would be a mono-substituted alkene. Okay, so at warm temperature, we get the most stable product, the most stable one, and this is the one with the more substituted alkene. Okay? Now, when we're doing this simple situation of just, the smallest 1,3-diene we could have, it turns out that the kinetic product, the 1,2 product is this, and that the thermodynamic product is the 1,4 product. Okay? That's not always true. Okay? So we're going to look at some examples now. We have to figure it out. Okay? So let's look at this top example. All right? So, like before, the first step, which is one of the most important steps here, is to decide where that diene would become protonated to form the most stable carbocation. Okay? So if we just number these 1, 2, 3, 4, on which of those carbons would the proton go to form the carbocation? 2. At 2?
1.
At 1?
So you said where the proton would go, right?
Where the proton goes on 2. Okay, so if the proton goes on 2, okay, it goes on 2, we would form a tertiary carbocation, right? Looks pretty good. Is that the best we can do? Okay, what did I say when we looked at the other position? Out of 4 different carbons where the proton could go, I said the proton is always going to go on one of 2 of those. Right? Is it going to go in the middle, or is it going to go on the ends? It's going to go on the end. All right? So look at that. We just put it on the middle. We got a tertiary carbocation. We got lured in, okay, by a quick payoff. But we didn't see the whole picture yet. Okay? So, we want to have a system that is allylic. We want an allylic carbocation that also spreads the plus to that tertiary position. Right? We want tertiary allylic, not just tertiary. Right? So where do we protonate to do that? At 4. Okay? So we're going to protonate over here. Okay, this gives us what doesn't immediately look to be the best carbocation, but when we consider its resonance contributor, this moves over this way, now it's looking a little better. Right? So by protonating at this out at position 4, we now have an allylic carbocation that's spreading the charge between the secondary and the tertiary position. That's going to be more stable than just that isolated tertiary carbocation. Okay? So this is going to be more stable. It's going to be the most stable carbocation. Okay, that we can form here. Yeah?
Would the next most stable be protonating number 1? Because then you get the allylic cation, but it's a secondary to secondary, not a secondary to tertiary.
Yeah, so good question. So this is where we get kind of close, right? So I would say that the next best position would be to protonate on 1. Right? That would be like the least intuitive place to do it, right? But then, like was just suggested, we get an allylic carbocation that's spreading the charge between 2 secondary positions. All right? Yeah.
We're just missing a carbon on your resonance.
I sure am. There and there. All right? So now let's draw the 2 products, right? The 1,2 and the 1,4 products. Okay, so if the bromide reacts at this end of the carbocation, right, that's going to give us the 1,2 product because the H went on the one just next to it. All right, so this is going to put the bromine here. This is the 1,2 product. Okay, and the bromide could also react with this end, oops, like that. And this would give us the (1,4) product. Okay? So, which of these 2 products would we generate as the major product if we were at a cold temperature? The one on the left, right? So this one we get at cold temperature. This is the kinetic product. Okay, we always get the 1,2 product at cold conditions, right? But that kinetic product has to come from the most stable carbocation. Okay? Both the kinetic and the thermodynamic products are going to come from the same carbocation. Okay, the same allylic carbocation. All right, so now, which of these 2 products is going to be formed as the major product at a warm temperature? Yeah, it's still going to be the same product. Okay, because notice that the one on the left has a tri-substituted alkene, whereas the one on the right is only a di-substituted alkene. Okay, so for this molecule, if we vary the temperature, we're still going to get the same product as the main product. So this product is also formed under warm temperatures. This is also the thermodynamic product. Okay? So, the key here, we have to figure out, 1, where do we protonate to form the most stable carbocation? 2, once we do that, what are our 1,2 and 1,4 products? We know the 1,2 product is going to be the kinetic product, but we have to evaluate the 2 products to determine which one would be more stable, so which one would be the thermodynamic product. Okay? Yeah, question?
Is it always an 80-20 or no?
No, of course, no. The question was, is it always 80-20? Every reaction is going to have some different ratio. Okay? And if you had temperatures at different than minus 80 and 40, they'd be different in between there as well. Okay? But what we're going to predict, though, is which one would just be the major product versus minor. Right? That's the best we can do. Okay? All right, so we'll pick up on Monday. We'll do this other example, and then we got one more reaction to do, in fact. Okay. Yeah.